Welcome to the 25th class meeting of EECE341, Introduction to Communication Systems. The most important announcement is on final exam, and it will be held on Friday, December 20th, from 7 p.m. to 10 p.m. At the next class meeting room. This room is already reserved by some other people, so I'm not sure whether it is available or not. If available, we may move back to LG 102. About voluntary project, many of you already contact me, and some of you have got my approval about the topic. And what is important thing is that your topic must be approved before you take the final exam. So it's not possible you contact me on Friday midnight and let me have this topic as my project, something like that. You can't do that. The due is on December 26th. I remember December 27th is the final day, the last day to finalize your grade. Messages from instructor. I forgot to emphasize the last one. In many of my classes, I talk about right side and left side buildings in electrical engineering. So left picture is the picture of the Petronas Twin Towers. Petronas Twin Towers in Kuala Lumpur, Malaysia. It's in the daytime picture. And in the night, you actually only see this single bridge here. But I added myself this using not the Photoshop, but just PC Paint. So many of you already know why I had added this ridiculously many bridges between these two buildings. This is what you are going to do as an electrical engineer. So even though you reside mostly on the right side of the building, you must communicate with the people in the left side building and vice versa. So in other classes, I usually put some final exam question about you stating what you learned in specific that course and relate what you learned as this right side and left side buildings in electrical engineering. So be well prepared. If you use LLM, they will just generate wrong answers, and I will regard your answer as fail. Got it? Corrections or clarifications. So this is no correction, but I need clarification. So last time when I talked about intersymbol interference, I give you easiest, simplest version, undergraduate version definition of intersymbol interference. And that actually works only for symbol time limited pulse shapes. And let me remind you what it was. So suppose here you have a transmitter. And here is your channel, continuous time channel, which admits a continuous time signal and outputs a continuous time signal. And here is your receiver. Suppose the signal here is a real bandpass signal, or for simplicity, let's say it's a real baseband signal. So real baseband. And output is also real baseband. And the input signal x of t is a signal that is similar to a line coded signal. So we may have something like this. Now, channel may distort or non-distort the signal, but let's consider the simplest case where you receive the same signal. Actually here, same means is not correct. Actually, distortion least channel output. But for simplicity, we set the attenuation factor, the unity, and delay 0. So what happens in this course? And also, we assume that P of t is a pulse shape that is time limited to 0 to capital T, which is the symbol time. So let's say P of t looks like this. Then what happens at the input to the receiver? You have the same signal. So your signal, depending on whether A sub n equals 1 or negative 1, you may observe something like this, right? 1, 1, negative 1, 1, 1, negative 1, something like that. This is an exemplary signal. So you should not regard y of t is always like this. So in this case, each pulse shifted by an integer multiple of symbol time does not overlap. So what can you say? Just looking at the graph or received signal, you may say that, okay, 1, 1, negative 1, 1, 1, negative 1 is received. You may say that. Now, what if you have the signal filtered by this channel? So in the second case, we assume that this continuous time channel is a linear time invariant system with impulse response h of t. Of course, h of t may be just a direct delta function with some delay, but let's say that this is a general h of t. Then what could happen? For example, p of t converted with h of t looks like, let me say, something like this. Got it? Then what will be the signal y of t? As you know, from the linear systems theory, the output may be written as, if we say this is q, then we have a sub n, q of t minus nt. So if the symbols were the same as the previous one, we may have what? We may have the first symbol contribution like that, and second symbol contribution like that, third symbol contribution, fourth symbol, fifth symbol, something like that. So the overall received signal may have, let's assume that there is no signal here, then you may have a little bit less, something like that. No, sorry. Here. Oops. Constructively interfering, and here destructively interfering, something like that. So do you see the difference? Due to this time domain spread of the pulse, what happens? The received signal becomes different. And here, if the channel is an identity channel, you have this pulse having same height, let's assume same, but here it is a little bit attenuated due to the effect of this zeros symbol. And you may say, I'm not saying that you must say, you may say that there is intersymbol interference, which means that there is interference among symbols. Got it? So this ISI may be understood in this way. But what I want to say is that the reason why I talk in this way is that many of the undergraduate students, when they first confront the notion of intersymbol interference, they understand this way. It is not completely wrong. That's what I'm saying. Got it? If you regard intersymbol interference, you understand this way, your understanding is very, 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 very limited. So most of the times, your understanding fails. That's what I want to say. Of course, this is correct in this special case, but not general. So let me give you another example. Suppose you transmit with P of t the rectangular pulse. However, your channel impulse response is also the rectangular pulse with same width. Now, what is Q of t in this case? Which is the transmit pulse converge with channel impulse response. As you learned in signal gen systems, you have a beautiful triangular pulse with width 2t, right? Now, I may ask you in the final exam to draw your input to the receiver, which is the output from the channel. And you will do almost the same thing as you did in the previous, this figure. So first, you have a triangular pulse with width 2t. You will have another triangular pulse with 2t, and another, and another, and another, right? Now let's sum up these pulses. What happens? Here, you have a straight line. And whenever you add up these straight lines, just focus on the edges, right? Because as you can understand, ax plus b plus cx plus d is always some ex plus f. Got it? So straight line. So what happens? Here, this plus that is 0, still this value. And here, this value plus this value is this value. So you have this flat signal. And if you keep continue, you will have something like this. Am I right? Now, let me ask you a question. Is there intersymbol interference? If you understand intersymbol interference in this way, you must say there is intersymbol interference because a pulse, overall pulse for A sub 0 overlaps with overall pulse with A sub 1, right? However, if you focus on what you are doing is digital communications, and suppose you sample at this point, that point, and that point. So if you sample at each integer multiple of t, then let's see what happens. You have some positive value, negative, positive, and you may decode these samples to recover, hey, I have A sub 0 equals 1, A sub 1 equals 1, something like that. So probably you decoded the data in this way, right? And of course, here, if there is no other interference or noise, you may say that, okay, still I have something like this. But what I'm saying is that here, there is no intersymbol interference. So when you talk about intersymbol interference, just overlapping pulses does not guarantee the existence of intersymbol interference. What is important is that when you sample the signal, whether there is intersymbol interference, so effect or contribution of other symbol contribution. Now, let me ask a silly question apparently again. Here, is there intersymbol interference? And many of you may say that, hey, you just said there is no intersymbol interference. But now, let's assume that you sample at integer multiple of t plus 1/4 of t. Now, do you have intersymbol interference? So let's see. So instead of sampling at capital T, you may sample here, right? So This is your value. Let me draw a square. Now here you have something like this. Blah, blah, blah. So is there intersymbol interference? It appears yes, right? So just looking at the continuous time waveform, you never can guarantee whether there is intersymbol interference or not. It appears that the existence of intersymbol interference does not only depend on the overall pulse shape, which is the convolution of the transmit pulse and the channel impulse response, but also your sampling instance, right? So given the same received signal, if you have some error or offset in your sampling instance, you suddenly have intersymbol interference. Got it? So never have this naive understanding about intersymbol interference. Intersymbol interference is not only related to the overlapping of pulse shape, but also related to the sampling instance. Got it? So be careful. Okay, where are we? We are studying chapter 5, and you know that today is the 25th class meeting. So this week we have 2 meetings, and next week we have our final class meetings. Of course, we have 2 more class meetings according to our rule book, but since we take the exams not during the class meeting hours, but in the midnight, I will modify your attendance on the 29th and 30th class meeting, and all your attendance is present. Got it? So don't worry about these 2 days. If something's wrong, please let me know. So we are going to cover the last part of chapter 5, and also we'll cover very briefly about information theory. I also have been giving you some shade or flavor of information theory and coding already, but I will briefly talk more about that. So last time I asked this question, as you remember. So given a bandwidth, finite bandwidth of your channel, how fast can you transmit data symbols or information bits? That is one of the most fundamental questions in communications and also information theory. Of course, information theory is not only about the data transmission. It is about also data compression and data transmission, where reliability and security does matter. Got it? Anyway, so information theory actually very mathematically answers to this question. Given a finite bandwidth on your channel, how fast can we transmit? Of course, reliably. If you reduce the reliability, you can increase your bit transmission rate, but that is not what we want. Something amazing about information theory is that given a mathematically well-modeled channel for communication, Claude Shannon introduced the notion of the capacity of channel. And this capacity is not total, not just related to capacitance or something. It's in Korean just the capability or something. So 용량, channel 용량 is what we say in Korean. So this capacity is mathematically defined in information theory as what? The maximum, actually supremum, but let me just use maximum transmission rate, transmission bit rate with arbitrarily small error. You may say this way. So amazingly, Claude Shannon discovered and proved that we may have communication system. We may design a communication system with error rate as small as we want. And also, in order to reduce that error rate, we don't need to make the transmission rate arbitrarily small. There is some finite value given some channel. So this is an amazing thing, and later you will see in information theory, one of the most important formula like this. So unlike Einstein's E equals mc square, it involves logarithmic function. So it's kind of different, but this is so-called the capacity of a band-limited additive white Gaussian noise channel. So this is the capacity formula for the additive white Gaussian noise channel with bandwidth W and spectral density N naught and the received signal power P. And you may not understand what does these parameters mean at this point, but what is important is this one. So if you increase the transmission power, you may increase the channel capacity given an additive white Gaussian noise channel. Of course, Shannon defined the capacity of a channel not only for AWGN. He defined for general communication channel, which is well statistically modeled. So if you increase the power, the capacity increases, but logarithmically. Now, it appears complicated, but actually your 수학 정석 and many high school math study aids has this one in your problem sets. Let me simplify. Some of you may remember you have seen some function looking like that. Actually, if you simplify that one, you have this one. And interesting thing is that when this signal defined for x greater than 0 is monotonically increasing function. So you may prove this, or you do it, or I may put it in the final exam, highly unlikely. Okay, so if you increase the bandwidth, given the same power and same spectral density of your noise, still you may increase the capacity of the channel. And it makes sense, right? If you have more bandwidth, which is the most scarce resource, important resource in communications, you can be benefited. You are never penalized, right? And also, if your noise level increases, your capacity degrades. And it makes sense. What is important is that this capacity can be achieved with arbitrarily small bit error rate. And it's amazing. Even though there is noise, you may effectively remove the effect of noise. And still, the capacity is positive, right? And Anyway, this is not an information theory course, so I'm not too much talk about it. But this is the most fundamental result. However, here goes the story. In this course, we are not talking about this capacity as the transmission rate. Got it? So when we ask the same question in this course without thinking about information theory, the answer is a little bit different. Because what we are going to do is that how fast can it reliably? So this reliably is defined differently. In information theory, arbitrarily small bit error rate. But here, what we say is that no intersymbol interference. Got it? In information theory, it does not say that whether intersymbol interference is beneficial or detrimental effect on our bit error rate. But here, we have little bit different definition about reliability of our received signal. So that's the difference. Never be confused. Now, there are too much explanation here, so let me skip and tell you. So suppose your received signal y of t is given in this way. Let me see. Just a sec. A and B. Last time, did I use A or B? Just a sec. Just a sec. Okay. B is logical bit. No, not B. Let me see. There it is. Okay. B is logical bit and A is real number. Got it. So I'm correct so far. Okay. So here I said A. Got it. So suppose your received signal looks like this, and you sample at every NT. Okay. Of course, you may add some delta, the sampling offset, but let's ignore for simplicity. Okay. And what you want is this one. When we sample at every NT, what do we have? Let me use N, M, M, M. What do we have? We have MT minus NT, right? What does this mean, by the way? For example, 0T. We have a 0 Q of minus NT. Just a sec. Yes, sigma. Let's do it step by step. So you have for n from negative infinity to positive infinity, you have something like this, right? And the next step is that since we focus on m equals 0 and we are interested in a sub 0, so for n equals 0, you have q 0. And for neighboring symbols, you have something like this. Am I right? See that? If you substitute n equals 1, you have a1 and negative t, right? a1, a sub 1, and q of negative t. And you have a2, q of negative 2t, a negative 2, q of 2t, blah, 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 right? Now, here goes the question. Is this sample of y of t sampled at 0t has intersymbol interference or not? Okay, that is the question. So here, this is the desired part. Am I right? And these are other symbol, intersymbol contribution. And if these are non-zero, then you may say their is intersymbol interference present in this sample. Am I right? So what would be the condition for zero intersymbol interference? So here goes the question. What is the condition on Q of t to have zero intersymbol interference? And of course, we may consider m equals 1. In that case, something like this, right? So we not only have to think about y sampled at 0, we also have to consider the samples taken at capital T, plus minus T, plus minus 2T, plus minus 3T. And how many cases do we have to consider? Apparently, countably infinite, right? To answer this question, we not only need to check for this sample, we have to check for this sample, y of negative t, y of 2t, y of negative 2t. However, do you see the same pattern here? What if these values are all zeros? Then if they are zeros, then these are also zeros, right? So actually, this condition can be restated. What is the condition on Q of t to have Q of plus minus t equals 0, Q of plus minus 2t equals 0, blah, 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 right? And of course, we may need this equals some constant. Okay, let me say A. So what we want is actually this one. Let's plot Q of t. Sometimes it was rectangular pulse. Sometimes it was this half sine pulse, truncated sine pulse. Or sometimes this triangular pulse. Sometimes this strange shaped pulse. But what is important is this one. If we ignore the sampling offset, what we want is that when sampled at plus minus t or with some offset, we have non-zero value, but all the t-spaced samples have zero value. Now let's go back to our triangular case. See that? If Q of t, this triangular Q of t, sampled at every t. Of course, you may say that, hey, at 0 it's 0, but we may shift the offset, right? So when we sample at every t, only one is non-zero, and all the others are zeros, right? And this pulse has zero intersymbol interference after we properly introduce the sampling offset, right? What about this pulse? You may say that, hey, if we sample at every t, then we have all zeros. But actually, you may introduce some offset, half t, then what happens? You have only one non-zero sample, and all the other samples are zeros. So this pulse also induces no intersymbol interference. Got it? So this is the key. When you uniformly sample the overall pulse Q of t, if there exists some offset delta, that gives you only one sample non-zero valued, and all the others zero valued, then you may have no intersymbol interference with that specific offset interval. Let's see some examples, not only that triangular pulse, but also some other pulses. So here goes so-called raised cosine pulse. And this is very confusing because this signal is actually related to cosine pulse. Raised means it's lifted up. Okay? So I have drawn here a function of f. Suppose you have cosine 2 pi f. Then it looks like that. Of course, you may have infinite periodic parts. But let's focus on a single period. Now, let's raise up this function. For example, you may have cosine 2 pi f, and you add 1. Right? Then this signal looks like that. Am I right? And now you cut out all the parts except this one and that one. And as the red sea divides, you may shift them to here and there. Got it? With the same distance. And you connect these two. This is the raised cosine spectrum. Got it? If your spectrum, a function of frequency, looks like this, made of this kind of cosine function raised up and shifted right and left, and you add flat sum parts, it is called raised cosine spectra. Got it? Now, if this is called a raised cosine pulse, is it unique? I've also shown you it exists, right? Is it unique? Of course not, because you may have different rate, different period for this cosine function. You may have different shift for this signal, right? So there are many possible raised cosine spectra, but in order to standardize, what we do is this one. We just find this point of symmetry. And we also find this flat part. And in order to standardize, what we do is that we normalize the entire spectrum so that this distance equals 1. Okay? So even though you may have different scale, if your two raised cosine spectra, if these 2 points of symmetry, distance equals 1 after proper scale, if they look the same also after proper scale on the y direction, usually they scale to 1. If they are the same, you say that they are same raised cosine spectra. So let me give you an example. If you have these two frequency functions, and I say that they are raised cosine spectra, are they classified as the same raised cosine function after proper normalization? Yes, because here they are raised but never separated to the right and left, and just scaling affects the shape. And also, there are special cases in the extreme. Are they raised cosine? Some people say, no. But some people say, yes, they are raised cosine with extreme case. And their extreme case means that actually this period converges to 0, which means that they are just goes down. So after proper scaling, they are the same thing, and they are raised cosine pulses in the extreme case. Now, what's the difference between these two and those two? That is so-called the roll-off factor. So here goes the term for raised cosine spectra. Roll-off factor is all about how fast your cosine function changes relative to this distance. So in order not to make everything complicated, let me give you the final story. So every raised cosine spectra looks like this. So you have flat top and raised cosine separated to the right side and left side. As I told you, this point of symmetry for this part and that part is important. So after proper scaling, this becomes negative 1/2, and this becomes positive 1/2. Now, due to the point symmetry with respect to these 2 points for each part, you have the same distance from negative 1/2 to this point and that point, and also same distance to this point and that point. And if you convert this one to 1 plus beta over 2, then this becomes 1 minus beta over 2, and this becomes negative 1 minus beta over 2. This becomes 1 plus beta over 2. Got it? So you can introduce a parameter beta so that this distance equals 1 plus beta over 2. Got it? Usually, beta ranges from 0 to 1. Of course, there are some research papers that successfully extended this conventional definition of raised cosine spectra, but usually the roll-off factor of a raised cosine spectrum is between 0 and 1 with the endpoints inclusive. Now, let's go back to our previous extreme case. What is the roll-off factor for these raised cosine pulse? Beta equals 0, right? Because from this point, you don't go over, right? So here you have beta equals 0. Now, what about these two? What about these two? It may be confusing, but according to the definition, this needs to be scaled to 1. Then what is this one? 2 and negative 2. Now, 2 equals, let me see, sorry, not 2. This is 1, right? See that? The distance is 1, which means that this is 1/2. And due to the symmetry, you have here 1 and negative 1. And this is 1 plus beta over 2. What is beta? Beta equals 1. So these two extreme cases, the roll-off factor is 1. Got it? So in one extreme, with rho factor 0, you have rectangular spectrum. When you have the rho factor on the other extreme equals 1, then what happens? You don't have flat top. You just have raised cosine. Got it? How much you stretch horizontally, how much you stretch vertically, it is a raised cosine spectrum with beta, the rho factor equals 1. By the way, rho factor is sometimes written in percentage. So beta equals 0 means 0%. Beta equals 1 means 100% rho factor. Now, this figure from the textbook shows the raised cosine spectra with different rho factors. As I told you, for beta equals 0, what do you have? You have this rectangular pulse with, after proper normalization, this value is 1/2, right? Now, on the other extreme with beta equals 1, what do you have? You have got it? So this is 1. This is -1. So beta equals 1. And beta equals 0. And there are uncountably infinite different raised cosine spectra taking different values between 0 and 1, different real values between 0 and 1. So there are many, uncountably many different raised cosine spectra. And what is their commonality? And very interestingly, in the time domain, so this is frequency domain, and this is in time domain, we have something amazing. See that? We want to sample, in this case, since we normalized, we want to sample at every unit time with possibly some offset. Now, what I am asking you is to find the offset. It may exist or not, but find the offset with which you have only one non-zero sample and all the other zero samples for raised cosine pulses. And amazingly, here at time 0 after normalization, you have a non-zero value. And here you have all zero values. Again, at -1, 0, and 0, and 0, blah, blah, blah. So actually, this family of functions called frequency domain, or just simply raised cosine pulses, have nice property. If properly sampled, it may introduce no intersymbol interference for pulse-shaped communication. Got it? So this is the raised cosine pulse. Got it? So one true false question around half of the students always lose is what? Just simply give this function. So here is a raised cosine function. Is this axis represent frequency or time? Got it? Frequency. Okay. If I draw a graph and saying that, showing something like this, that periodically 0 crosses, and I say that this is a graph of raised cosine pulse. What is the horizontal axis? What horizontal axis represent? Time. Got it? Never forget that. This raised cosine. This cosine function raised is performed in the frequency domain. Never forget. Okay? You may say that I will never forget, but amazingly, many graduate students has misunderstanding initially when they take digital communications. Now, let's little bit generalize this idea of raised cosine pulse. Do we have other pulses, other family of pulses that satisfy this condition of zero intersymbol interference when the pulse is uniformly sampled with some proper choice of sampling offset? Actually, we can generalize this one, and that is called Nyquist pulse. So let me draw a Venn diagram. Here goes pulses. So suppose you have a set of pulses for symbol transmission rate 1/t, which means that you want the signal look like this. Let me use Q. Ready? So this means that. And inside this big set, you have a very small but important subset. And this set is called the set of Nyquist pulses for symbol transmission rate 1/t. And inside of this subset, you have raised cosine pulses for symbol transmission rate 1/t. And these signals must look like this in the time domain. Now, something like this. And also, this signal looks similar to that after proper choice of sampling offset. But some pulse here may have some non-zero samples, whatever offset you choose. In this case, this pulse is here, which means that this is not a Nyquist pulse. Got it? So Nyquist pulse for symbol transmission rate 1/t is a kind of generalized version of raised cosine pulses for symbol transmission rate 1/T. And now we have defined this one, hoping there exist many other important pulses. And actually, you already know one of them. And that is so famous, and you already have in your mind. That is what? That is the sync pulse. So sync pulse after proper scaling, what do you have? But some of you may say that, hey, professor, you are wrong. Why? Because since we define raised cosine pulses for parameters beta between 0 and 1 with endpoint inclusive, actually, sync pulse with spectrum look like this is what? The extreme case of raised cosine pulse with roll-off factor 0, actually. So this is there. Okay. So this pulse, sync pulse, is actually a raised cosine pulse. Got it? With roll factor 0%. So it seems that, is there any other pulse? The answer is still yes, other than sync pulse and a square raised cosine pulse. And Nyquist derived the condition for a pulse to be a Nyquist pulse. Got it? So here goes the theorem. The theorem is very simple. According to our notation, Q, this is the notation. So let's say that Q of t has the continuous time Fourier transform capital Q of f. Then Nyquist theorem says that Q of t is a Nyquist pulse. Let me state. Q of t is a Nyquist pulse for transmission rate 1 over t, if and only if Q of t, Q of f, which is the inverse Fourier transform of this pulse Q, satisfies what? Sigma capital Q f shifted uniformly equals some constant for all f. Okay. This is the theorem by Nyquist. So Q of t is a Nyquist pulse for the symbol transmission rate 1 over capital T, if and only if the pulse is continuous time Fourier transform after shifting. See that? This is shifting by, if you don't want negative, shifting by integer multiple of capital T, the symbol transmission rate. See that? This one matches with that one. Okay? It's constant for all f. By the way, we have a name for the left-hand side. This is so-called folded spectrum. And it will be obvious if we re-examine this theorem with our friend raised cosine pulse. So let's check whether this theorem is correct or not. So for raised cosine pulse, what did we have? For transmission rate 1 over t. Here goes 1 over 2t, and here goes negative 1 over 2t. Because now we are thinking about raised cosine pulses for transmission rate 1 over t. So we have some 1 plus beta of now 2t, and here negative 1 plus beta over 2t, and here negative 1 minus beta of 2t, and here we have 1 minus beta of 2t. And here we have flat, not here. Here we have some flat part and what? Raised cosine part. So we have points of symmetry, and here goes the roll off or fall off. Roll off means that it slowly diminishes, got it? It decreases. Now, this is Q of f for our raised cosine with some beta positive and less than 1, right? If beta equals 0, we have brick wall. If beta equals 1, we have no flat top. So obviously, this spectrum has roll factor between 0 and 1. Now, what is the Nyquist theorem? You have Q of f, and you shift this spectrum left by your symbol rate, related symbol rate 1 over t, right by 1 over t, right by 2 over t, left by 2 over t, something like that. So let's draw. So here is the origin, and this is 1 over t, and then here you have 2 over t, which is 1 over t. Now let's draw and see what happens. Since you are very clever students, getting almost all A's in high school, you can easily draw this one. And also, for that part, you can draw something. So this is the right shift by capital 1 over t. This is left shift by 1 over t. Now you do the same for 2 over plus minus 2 over t, 3 over t, 4 over t, and add up, sum up. Now here goes the question. Is this f of a q of f after spectrum folding? Is it a constant function for all f? And your answer is yes, right? This gives you a constant folded spectrum. So raised cosine pulses are Nyquist pulses. Got it? Got it? Raised cosine pulses are Nyquist pulses because it satisfies the necessary and sufficient condition. And now let's go back to our prior question. Is there any other pulses that satisfies Nyquist condition? And we already know the triangular pulse must be a Nyquist pulse, right? And what is the triangular pulse's spectrum? So let's see. To make everything simple, let's little bit shift our triangular pulse. So we have t, negative t. This is q of t for triangular pulse. Now, what is its Fourier transform? From our knowledge that triangular pulse can be obtained by convolving rectangular pulse and itself, right? Actually, time shifted, time reversed. And we know that rectangular pulse in time domain is a sync pulse in frequency domain. What do we have? Suppose this is p of t convolved with p of negative t. And p is sync pulse. So its conjugate is the same. Then what happens? According to our convolution theorem, convolution in time equals multiplication in frequency. We have what? This one, for sync pulse. So this is sync pulse, right? How to say it? This is rectangular with sync spectrum. And this is sync spectrum squared. So what we have is actually something interesting. And you can easily find that each zero touch occurs at every integer multiple of 1 over t. And here goes something amazing. Now let's shift this sync square pulse by every integer multiple of 1 over t and sum up. What will happen? What do you think will happen? Amazingly, you have a constant. Okay. So this triangular pulse in time domain, after proper sampling offset taken, it's a Nyquist pulse for the transmission rate 1 over capital T. For the derivation of Nyquist theorem, I do not want to talk about it. It'll take more than 30 minutes and it confuses. And you go back to this topic in the next course, digital communications. If your professor does not derive and saying that, hey, you learned, you say, no, professor just mentioned this theorem and never proved, and please prove it in the classroom. Ask him, got it? And you will be amazed by how much the proof is beautiful. Anyway, so the key is this Venn diagram, got it? So here is the set of pulses, Q of t's. That set is for the transmission rate 1 over t. Inside the set, you have a very small subset called Nyquist, set of Nyquist pulses for the transmission rate 1 over t. What does that mean? After proper sampling offset, and you sample at every capital T, integer multiple of capital T with same offset, you have only single non-zero value and all zero values. This is the set definition of Nyquist pulse. And you have smaller set called raised cosine pulses. Got it? And sync pulse, unfortunately, is actually the extreme case of Nyquist, raised cosine pulse. However, here you have triangular pulse with width 2t. Got it? And the theorem says sync square shifted uniformly by this zero touch integer multiple of zero touch interval gives you what? A constant. After summing up all these countably infinite sync square pulses. It's amazing. And actually, this is one of the reasons why OFDM signal looks flat at the center of the subcarriers. Of course, some of you already know what is OFDM and cyclic prefix. If there is non-zero cyclic prefix, actually, you shift these sync squares not by this zero touch intervals integer multiple. So actually, you have kind of wiggling on top of the spectrum. Anyway, that is the topic of advanced digital communication. So never expect that appearing in the final exam. But this is very important. Sync squares properly shifted and added up gives you a constant function. So far, so good. Now, there is another important corollary. And this corollary is also about Nyquist pulse. Got it? So here goes the story. There are two Nyquist theorems for undergraduate students. One is for Nyquist sampling theorem. What was that? Nyquist sampling theorem. You must distinguish these two theorems. At your age, I couldn't. You do it, got it? Sampling theorem is about sampling and perfect reconstruction. Zero ISI theorem, I just have shown you, is all about what? Symbol transmission. And when sampled uniformly, generating zero intersymbol interference. And these two theorems so far look similar. Why? Because as you remember, sampling theorem also involves what? Spectrum folding. Many of you may remember already, right? And also, this zero ISI theorem also involves spectrum folding. But the difference is there. What? In sampling theorem, what you wanted is that folded spectrum when folding occurs, there is no overlap actually. But here in zero ISI theorem, overlap is okay as far as what? Resultant folded spectrum is constant. Got it? Now, one of the corollary in Nyquist sampling theorem is what? The necessary condition. It is necessary to have what? The sampling theorem, this is sampling rate for this sampling theorem, is greater than or equal to twice the bandwidth of the signal to be sampled, right? So if this is the message signal spectrum, this is W, and this is 2W, and what you want is that your sampling rate is greater than or equal to twice the bandwidth of the signal. Otherwise, what happens? Aliasing occurs. When you generate folded spectrum, you add up non-zero two values. Let me ask you a question. I have two numbers added and result is 5. Find the two numbers. Can you do that? No. There are infinitely many combinations. That's why we cannot perfectly reconstruct the signal when aliasing occurs. So this is no aliasing condition. Necessary condition, right? It is necessary. And here, the corollary for zero ISI. Amazingly, Q of F, suppose Q of F is band limited with bandwidth W. Then you need the inequality exactly opposite. Why? See that? Suppose this is violated. So this is satisfied. What happens? You have W, and you have 2W, that is less than 1 over T. What happens? So here is your 1 over T. Now you shift by 1 over T, and negative 1 over T, 2, 3, right? So if Q is band limited, in order for that pulse to be a Nyquist pulse, you must satisfy this condition. That has exactly opposite direction in the inequality to the Nyquist sampling theory. They have different results. Why? Because they are talking about different things. But many undergraduate students, even 30 years ago, me, had no idea whether they are different or not at all. Got it? You don't do this. See that? If you have band limited signal, after folding, no overlapping, how can it be flat? Impossible, right? That's why you need this condition, exactly opposite to your Nyquist sampling theorem. So it's very interesting. Looking similar theorems is contributed by the same person, Nyquist. And he derived interesting, necessary, and sufficient conditions. There are two theorems, and two theorems has two corollaries, necessary conditions. And they look very similar, but with opposite directions in the inequality. Okay, so this is all for today's meeting. And probably in this Wednesday's class meeting, I will talk a little bit more about Nyquist theorem because we have something to say more related to a matched filter. But after talk about that, we will more focus on a big picture, the information theory. That's all for today.